Well, hello, class.
Hello.
Hello. Hello.
Hey, sweetness.
Well, you might think about, before you get into solving systems of linear equations, taking the time to review what you know about solving systems of equations, not with derivatives in them, just regular equations, and also recall what we did with differential equations involving differential operators. So, a system of differential equations is more than one with the same functions and derivatives. Okay, here's two equations with a derivative dx dt and a derivative dy dt and a function x and a function y, and here an x and there a y, and everywhere a y. So, a solution for such a system is a set of sufficiently differentiable, in other words, we've got to be able to have enough derivatives that they could be plugged into our original system, but functions f1 of t, f2 of t, etc., that satisfy the system on some common t interval I. So the strategy is going to be a lot like something we do in algebra, elimination and determinants. If you have access to my Precalculus 1 website, look up solving systems of equations by determinants and also by elimination. That might be helpful. So, the complicated part of this is actually going to be finding the relationships between the constants. For instance, in this equation, we got a first derivative in x and a first derivative in y, so we got to expect that our answer would have two constants, one for the x, one for the y. And that's typical. If this would be a second order and not a first, it would need three. But sometimes when we go through the process of solving these, we get more than that. So we have to figure out a way to find relationships between the constants so we can cut down to the proper number. So, let's just start by saying we're going to be looking at using operators as a method to solve these. And so our first task is take this system, this equation and this equation, and write them both in operator notation. Okay, I'm going to go. This is a second derivative, so that means d squared plus a first derivative of y equals negative 5 times x. So a second derivative, you know what, I'm going to add this 5x to both sides. It would be d squared x over dt squared plus 5x plus dy dt equals 0. And look, that's what this operator notation says. D squared plus 5, that's second derivative, plus 5x applied to x, right? Plus first derivative applied to y equals 0. Okay, the second one, notice this x and this y on this side of the equation. I'm going to add x to both sides. I'm going to subtract 4y from both sides. And if I do that, then derivative operator, differential operator plus 1 applied to x would be like dx dt plus x, see? And then subtracting 4y from both sides would be plus differential operator minus 4 applied to y equals 0 on the right. So there, this differential equation system is written in operator notation. Now you might not know why we want to do that, but it's coming. So, part 2, write this one in operator notation. Well, this is interesting, but it's e to the t. That might make it a little more interesting, but in fact it really doesn't make it much more interesting. It's just derivative of x plus the derivative of y equals e to the t. Not much to that. And this one is a little more complicated, so negative of the second derivative of x plus the first derivative of x plus 1 plus just the function y equals 0. So there that one is, all factored out beautifully. Notice I put it in parentheses, so it's switched this sign and this sign, this negative sign, this negative sign, because I factored out that negative sign. But there it is. There is this system written in operator notation.
Do you like it?
Yeah, I like it.